Hello students, this is Mr. Elliott, your favorite science teacher. I'm here to give you a quick review lesson over chemical bonding. And of course this relates to chemical reactions, and here's my good friend Mr. James Bond to get us started. He's standing next to his nice car, his Aston Martin. I think they used that one and shot it up in his recent movie. But so be it. That's what happens sometime. Chemical bonding. Well, why are we studying chemical bonding? Because that's what chemical reactions are all about. In fact, when you have a chemical reaction, all you're doing is you're breaking and forming the bonds down at the atomic or molecular level. Well, here's some information we want to look at. Here is an atomic model of the element boron. Now look at the number of protons. It has 5 positive protons. It's got 5 negative neutrons that balance out, of course, and cancel out that charge since it's an atom. But here we go. The thing we're focusing on with chemical bonding are what's called the valence electrons. These are the electrons in the outermost energy level. Now when we're talking about the outermost energy level, we're talking about these things where the electrons float around the nucleus. I've heard them called energy levels. I've heard them called electron shells. I've heard them called electron orbitals. And I'm trying to use those terms interchangeably here. It's the number of the electrons in that outer shell, or the number of valence electrons, that determine how and if an atom's going to bond or not, or how powerfully the reaction will be. Okay, looking at boron here, you can see that it only has 3 valence electrons, because those are the electrons in the outer shell. Well, the way the electrons are configured in these atoms, it basically follows some rules or patterns. And here's what you need to know. The first shell can hold up to 2 electrons and no more. So if it has 2 in its first shell, then that shell is full. If it only has 1 shell, then that shell is full and it's not going to bond. But most of the atoms that we look at are going to be bigger than that. So they're going to have at least a second shell, and some of them have more than that. So the other rule is that the second shell can hold up to 8 electrons. Now the third shell and fourth and on and so forth and so on, they can hold greater numbers than that. But let's focus on, for our purposes, on 2 and 8. And 8 is our magic number, because most things that we deal with are going to have up to 8 in their second shell, or in their outer shell. Little spin for you. There you go. Alright, so here we have a diagram showing 4 different atoms. On the left we have hydrogen, then carbon, then nitrogen, then oxygen. Now look at the diagrams and look at the valence electrons, the electrons in the outer shells. And they've left little faint circles there so you can see when it's lacking stuff. Well, first let me tell you about the octet rule. This is known as the rule of 8. Octet means 8. You think of an octagon as 8 sides. Well, what this is saying is that atoms tend to gain, lose, or share electrons so they can end up with 8 valence electrons in their outer shell. That's a general rule. For some reason, they want to get a full outer shell, and they're trying to get that full outer shell to be 8. Of course, one exception is a small atom like hydrogen. It doesn't have a shell of 8 because it only has 1 shell. And the 1 shell can only hold 2, so if you see this, it only has 1 valence electron, therefore it can gain 1, and then it would have a full shell. So hydrogen will indeed bond because it wants to gain that 1 electron. But if you look at carbon, carbon has 4 valence electrons. That means it can gain 4 more to get 8. There's your rule of 8. So it will definitely bond as well. Nitrogen has 5 valence electrons, so it can gain 3. Well, again, back to the rule of 8. It wants to have 8, so it will also bond to try to get those other 3. Oxygen has 6 valence electrons. It can gain 2 more to get 8, and so it will also bond. Chemical bonding, it's really all about trying to get those outer shells full. And there are 3 types of bonds. There's ionic bonds, covalent bonds, and metallic bonds. And each one is a little bit different. Let me explain. In an ionic bond, that's when you have a transfer of electrons. You know, it's like maybe one atom steals an electron from another and then they kind of hook up. In covalent bonds, they share, they play nice, okay? I think of it like this, you know, covalent's like they're cooperating. It's easy for me to remember it that way because you think covalent, you got your CO, your co, or your cooperate, okay? They're sharing electrons. In metallic bonds, well, I guess you could say this is also a kind of sharing, but it's a different scenario. When I think of covalent bonds, I'm thinking of just onesies and twosies. In metallic bonds, inside a metal substance, you have an excessive number of electrons just kind of floating around in there like a sea of electrons, and so it's easy for the atoms to get the electrons they need for those shells. I'll show you some diagrams that will clarify this. For instance, here's a little animation about ionic bonds. Notice the chlorine atom on the right, the green one, needs one electron. The sodium atom, the Na, on the left, has one, so it transfers it or takes it from it, and then they bond together. On the other hand, here's covalent. This is when they cooperate. I'm not sure what atoms these are representing or what elements, but it looks like each one of them needs one electron, and so they're hooking up and they're just going to share, they're going to cooperate. They're bonded together. Now here's our metallic bonds, and I told you it's like a sea of electrons. If the little red dots are the electrons, you see there's just a lot of electrons floating through this matrix of this metallic structure, and so it's easy for the atoms to get the electrons they need. Well, this concludes our quick review on chemical bonding. Thank you 007 for helping out, and rock on.